Over the next few videos, we're going to be talking about enzymatic reactions. One of the coolest things enzymes do is speed up reaction rates. And so we're going to be asking the question, well, how do enzymes speed up reaction rates? But I realized as I was preparing that we actually needed to take a step back and ask the question first, like what determines reaction rates in the first place? So that is the goal of today's video. When I have taken various workshops and courses on teaching and pedagogy and everything, one of the things everybody says with is you should always lead with complicated looking equations because that just invites students in. Okay, maybe not, but I am a huge fan actually of math, and I'm a huge fan of understanding what equations mean. So this is actually what we're going to be looking at today, maybe in a way you haven't looked at it before, and that is the Arrhenius equation. I have this blank slide here because actually, rather than working on the Arrhenius equation as a starting point, we're actually going to start with an experiment with my cat. So let's switch over to that. Well, hello. Here we are doing the experiment. Harriet here, my cat's going to help me out. Harriet, it turns out, Harriet, turns out she really likes chicken. And what we're going to do is, here's the rules of the game. I have the dice, and every time I roll a 6, Harriet gets a piece of chicken. Oh, you got a 6. Look at that. There's some chicken. And I'm going to keep rolling the dice and ask, how quickly do I get chicken into the cat? Keep rolling the dice, keep rolling the dice, keep rolling the dice, keep rolling the dice, keep rolling the dice. Oh, we got another 6, cat. There's another piece of chicken. Hey, look. Okay, so we have our experiment with my cat, who was a good sport about this whole thing. What we're going to be thinking about is what determines the rate that the cat gets chicken, right? And it turns out it's based on 2 basic things. It's how often do I roll the dice? And in this video, I actually rolled the dice 10 times in 13 seconds, which means I did 0.77 rolls per second. And then what's the probability of rolling something that gets chicken? In this case, a 6. That's a 1 in 6 on a fair dice, right? And I can just multiply these together and I can say, all right, well, the rate that I'm going to get chicken into the cat is 0.13 chickens per second based on just multiplying these 2 things together. Okay, cool. Hopefully that is relatively straightforward. Let's go back to our scary looking equation. It turns out that's all that this is doing. So what is the rate that the cat gets chicken? That is our rate constant. That says what is the rate, the intrinsic rate of this reaction. How often do I roll the dice? That's what the A prefactor is. And what's the probability of rolling a chicken? Well, that's this e to the minus whatever, Arrhenius over RT, Arrhenius energy over RT. In chemical terms, this translates to, well, what is the rate of a reaction? K. How often do reactants collide? And then if the reactants collide, what is the probability that they actually cross the energy barrier? And it turns out that those chemical features are directly identical or directly equivalent to the cat features. So now what I'm showing here is a movie. It's a simulation that I ran of just a methyl carbon sitting there. And you'll notice is I've colored all of the hydrogens different colors. And what you're seeing is it's sitting there and wiggling around, bouncing around back and forth. What we're thinking about is what's the rate of bond rotation, particularly this bond here. And that's given by how often does it try to start spinning. Turns out that's about 10 to the 13th per second. And then what's the probability it has enough energy to get over the eclipse? Oh my goodness, it just did it. I don't know if you saw that. We're going to go back and watch that in slow motion. But basically, the green just hopped over into this position here. So what's the probability it has that energy? So here's that move in slow motion. We're seeing it going from green, crossing the eclipse state, and then going into the other staggered state. And we would describe this in the following way. We can go from staggered to eclipse to staggered. And there's some activation energy associated with that. In this case, it's 13 kilojoules per mole to go across this energy barrier. Again, going back to the cat analogy, that is telling me something like what's the probability of rolling a 6? It's what's the probability that I get a big enough whack of energy from the thermal energy in the system to go from staggered through eclipse to staggered. And that is, if we plug in our numbers here, so e to this whatever else, gives us our probability of this happening is 1 in 90, basically. So for every 190 attempts on average, we expect to go over this barrier. Okay, at room temperature, or standard temperature. Okay, so what's the rate of reaction? How often do reactions collide? What's the probability that they cross the barrier? We can plug in those numbers. So we got that. The energy barrier is 13 kilojoules per mole, so it's a 1 in 190 chance. We're attempting this every 10 to the 13 times per second, which means that if we were to say do an experiment, we could measure this rotation rate, and that rotation rate would be on the about 2 to the times 10 to the 11th per second. Okay? So what's determining the rate? Well, it's how often do we try to do stuff times how probable is it to do the thing. Okay. So that's what I got on this, actually. That's a quick summary of how to think about where reaction rates come from. Because when we start talking about enzymes, we're going to start saying, well, look, they sped it up. How are they going to speed it up? What sorts of things can they change? And that's all determined by this basic Arrhenius relationship. So hope that was useful, and I will talk to you later.